Hey guys, this video will be on Introduction to Functions. We're going to start with some definitions. So consider a table of some ordered pairs. A set of ordered pairs is called a relation, and the set of all x-coordinates is called the domain, and the set of all y-coordinates is called the range. Equations in two variables are also called relations, since we can define a set of ordered pairs for them. Let's do an example. We want to find the domain and range of the given relation. Again, the domain is the set of all x-coordinates, and the range is the set of all y-coordinates. Our x-coordinates are these values, therefore we list these in our domain. And notice that the 3 repeats. We actually don't need to list this twice, so we can just list this once. And we could also put these numbers in order if we wish. Therefore, our domain for this relation is -1, 0, and 3. The range is just the y-coordinates. Putting these values in order, we have -2, 0, 2, and 3 for the range. Okay, let's define what a function is now. A function is a set of ordered pairs in which each x-coordinate has exactly one y-coordinate. In other words, a function cannot have ordered pairs with the same x-coordinate but different y-values. So for this example, let's determine whether the relation is a function or not. First, we should check if an x-coordinate appears more than once, and if so, they should have the same y-coordinate in order to be a function. It looks like we don't have any x values that repeat, so we won't need to investigate the y value. This set of ordered pairs is a function. Now for part B, again, we want to check if an x-coordinate appears more than once. 0 actually appears twice, so now we have to see if the y values match for this x-coordinate. The y values are actually different. Again, a relation is a function if each x-coordinate has exactly one y-coordinate. But our x-coordinate of 0 has 2 different y-coordinates, -2 and 3. Because of this, this relation is not a function. Relations and functions can also be described by graphs of their ordered pairs. So for example 3, let's determine whether the given graph is a graph of a function. So does each x-coordinate have exactly one y-coordinate? If it helps, we can organize these ordered pairs in a table. Notice that our x value appears just once for this relation, so we don't even have to check the y value. We can right away say that this graph is a function. Now let's determine if this graph is a function or not. Again, we can list our ordered pairs in a table. For this relation, we actually have the x-coordinate 1 appear twice. Now we have to check if the y values match. However, they are paired with 2 different y-coordinates, so they are not matching. And because of this, this graph is not a function. By the way, if you look at the graph, notice how there's more than one point at the x-coordinate of 1. This will always be the case when the graph is not a function. So if you draw a vertical line at every x-coordinate, there should only be one point in order to be a function. Therefore, for graphs, you can use a vertical line test to determine whether it is a graph of a function or not. Let's write down this test. So if a vertical line can be drawn so that it intersects a graph more than once, then the graph is not a graph of a function. Let's try using this test for the following examples. So if we run a vertical line from left to right, notice how it only intersects the graph just once. This graph passes the vertical line test. Therefore, this is a graph of a function. The same thing for the next graph. Running a vertical line from left to right, it only intersects the graph once. This passes the vertical line test. Therefore, this is a graph of a function. However, for the next graph, we can right away see that the vertical line intersects the graph twice. This does not pass the vertical line test. Therefore, this is not a graph of a function. And the same thing for the next graph. Running a vertical line from left to right, it intersects the graph many times at this x-coordinate, which makes sense since it's already a vertical line. So this does not pass the vertical line test, and therefore is not the graph of a function. So recall that a graph of a linear equation in two variables is a line, and a line that is not a vertical line will always pass the vertical line test. All linear equations are functions, except those of the form x equals a, which is a vertical line. So for example, y equals x is a function, y equals 2x plus 1 is also a function, and so is 3x plus 2y equals 5. But x equals 2 is a vertical line, therefore not a function. And y equals 2 is a horizontal line, and this also would pass the vertical line test, therefore this is a function. Okay, so next we will discuss how to determine the domain of a relation written as an equation. Remember, the domain is the set of all x-coordinates for a relation. Sometimes it is helpful to ask yourself, is there any number we cannot substitute for x? Let's try an example. We want to determine the domain for the following relation. Notice that this is the equation of a line. And since domain is the set of all x-coordinates for this equation, we need to figure out what numbers we can plug in for x. So we can actually plug in any number for x and always get a value for y. Therefore, the domain for this equation is the set of all real numbers. We can also write the domain in interval notation. The values for x range from negative infinity up to positive infinity. Okay, for the next equation, again, we need to figure out what numbers we can plug in for x. However, for this one, it's better to ask if there is a number that we cannot plug in for x. So since this is a fraction, we can never divide by 0. So our denominator x cannot equal 0. All other values are okay. Therefore, our domain will be all real numbers except x equals 0. And to write this in interval notation, it might be helpful to see a number line of the x values that are allowed. So we'd have an open circle at 0, since the domain cannot include 0, and then shade everything around it. So our interval notation will be from negative infinity up to 0, but not including 0, so we use parentheses, union 0 to positive infinity. For the next equation, we have another fraction. So all values of x will be fine as long as the denominator is not 0. So we need to find the value of x that we cannot substitute in, meaning the value of x that will make the denominator equal 0. So let's find this undefined value. We can set the denominator equal to 0 and solve for x. and then we get x is equal to 3. And our equation will be undefined when x is equal to 3. Therefore, our domain is all real numbers except x equals 3. And for our interval notation, the values of x are from -infinity up to 3, but not including 3, union 3 up to +infinity. Okay, one last thing to go over. We can actually name our functions using function notation. So consider the functions y equals x plus 3 and y equals -2x plus 4. To write these equations in function notation, we can use letters to name them. We can use f for the first equation and g for the second equation. We read this as f of x and the other as g of x. These equations mean the exact same thing, and so do these. So y is the same as f of x, and this is called function notation. And we read this as y equals f of x, meaning y is a function of x where y depends on x. So consider the function f of x equals x plus 3. Really, this is just a fancy way to write y equals x plus 3. So just know that both ways can be used interchangeably. We can also evaluate functions. So for example 6, let's evaluate the function for the given value. All we need to do is substitute 2 in for x of the function. And we get y is equal to 5. This question could have also been written in this manner, where we want to find f of 2. This is actually the same problem, just written in function notation. So again, all we do is substitute 2 into our function for x. And we also get an answer of 5. So f of 2 is equal to 5. Let's try another example written in function notation. So let f of x equal x squared minus 8x plus 3. And we want to find the following function values. So for f of 3, we want to substitute 3 in for our x of our function. So f of 3 equals 3 squared minus 8 times 3 plus 3. Simplify this, and we get -12. Therefore, f of 3 is equal to -12. And for f of -1, we substitute -1 for x of our function. Simplify this, and we get 12. Therefore, f of -1 is equal to 12.